Hello everyone, my name is Meenakshi. I am from BSc Chemistry Honors second year. Today my topic is electrochemistry. Give the postulates of Arrhenius theory of ionization. The main point of Arrhenius theory are given below. When dissolved in water, an electrolyte splits or dissociates into positively and negatively charged particles called ions. This process is called electrolytic dissociation or ionization. N- NaCl dissociate into Na positive plus Cl negative. MgCl dissociate into Mg2 positive plus 2Cl negative. Al2SO4 3 dissociate into 2Al3 positive plus 3SO4 2 negative. On passing electricity, the positively ions migrate toward the cathode and are therefore called cations. Similarly, negative ions called the anion move toward the positively electrode with anode. The solution of the electrolytic is electrically neutral as a whole. That means total charge carried by the positively ions is equal to the charge carried by negative ions. The ions obtained by dissociation of the electrolyte combine back to give the undissociated molecules. Ultimately, an equilibrium is reached between the ion and the undissociated molecules. NaCl into Na positive plus Cl negative. The fraction of the total number of molecules of the electrolyte that dissociate into ions is called the degree of ionization or dissociation. It is usually denoted by alpha. Example, degree of dissociation is equal to number of molecules dissociate by total number of molecules taken. The degree of dissociation increases with dilute and becomes maximum at the infinite dilution. The conductance of an electrolytic solution is due to the presence of the ions produced by the dissociation of the electrolytes. Greater the dissociation, the higher is the conductance. The property of an electrolyte are the property of its ion. For example, the properties of an acid are due to the H positive ions furnished by it in the aqueous solution. Similarly, the property of a base are due to the OH negative ions produced in the aqueous solution. The ions produced by the dissociation of an electrolyte behave like molecules toward colligative properties. For example, each NaCl molecule dissociates to give two ions with N positive and Cl negative. Hence, the observed value of any colligative property is double the expected value. What are the factors that govern degree of dissociation of an electrolyte? The degree of dissociation of an electrolyte in the solution depend upon the following factor. Number 1. Nature of the solute. Some electrolytes like minerals, acid, alkalis and most of the salt are almost completely ionized in water. These are called strong electrolytes. On the other hand, some electrolytes like organic acid and bases and some inorganic acid and bases ionize only to a small extent. These are called weak electrolytes. Second, nature of the solvent. Every solvent has some definite value of the dielectric constant, which is defined as its power to weaken the force of attraction present between the ions of the electrolytes. Water has the highest dielectric constant. Those the dissociation of an electrolyte is maximum in water. Third, concentration. Degree of dissociation of an electrolyte increase with dilute and becomes maximum at infinite dilution. Example, zero concentration. Fourth, temperature. As the temperature is increased, more of the molecules split into ions. Example, degree of dissociation increase. Fifth, presence of common ions. The degree of dissociation of electrolytes decreases when another electrolyte is present which furnishes a common ion. This effect is called common ion effect. For example, dissociation of NH4OH decreases in the presence of NH4Cl negative. The following give evidence in support of Arrhenius theory of ionization. The following evidence lends support to the theory. Electrolytic conductance. Arrhenius theory say that the conductance of the solution of an electrolyte is due to the presence of the ions produced by an electrolyte on dissociation. Strong electrolytes possess high degree of dissociation and hence show greater conductance, whereas weak electrolytes dissociate to a small extent and hence show low conductance. Variation of conductance with dilution. It is observed that the specific conductance decrease whereas conductance as well as equivalent conductance increase with dilution. The explanation is evidently based on postulates of the Arrhenius theory. The equivalent conductance and the dissociation of the electrolytes vary in such as similar manner with dilution that the degree of dissociation alpha of the electrolyte at any concentration can be expressed in terms of equivalent conductance as follow: alpha is equal to lambda c by lambda 0. Note: where lambda c is the equivalent conductance at the given concentration and lambda 0 is equivalent conductance at infinite dilution. Electrolysis. According to Arrhenius theory, an electrolytes when dissolved in water dissociation into ions, thus the function of the electricity is only the direct the ions toward the electrodes. Colligative properties. Anomalous results are obtained while measuring colligative property like osmotic pressure, elevation in boiling point, etc. of the strong electrolytes. This is because every ions produced from the electrolytes act as an independent particles as per as colligative property are concerned. Ionic nature of reaction. According to Arrhenius theory, the property of an electrolyte are the property of its ions. Thus, the reaction between NaCl solution and EgNO3 solution forming a precipitate of AgCl may be explained as follows. NaCl NaCl in aqueous solution ionizes as NaCl is equal Na positive plus Cl negative. AgNO3 also ionizes in aqueous solution as AgNO3 Ag positive plus NO3 negative. When the above two the solution are mixed, we have Na positive plus Cl negative plus Ag positive plus NO3 positive react as AgCl plus Na positive plus NO3 negative. The reaction between any two ionic compounds in aqueous solution take place in a similar manners. Heat of neutralization. The heat of neutralization is defined as the amount of heat evolved when 1 gram equivalent of the acid is neutralized by the base or 1 gram equivalent of the base is neutralized by the acid. The heat of neutralization of a strong acid with a strong base is always the same, with 13.7 kcal or 57.3 kilojoule. This is explained by the Arrhenius theory as follows. Suppose the strong acid is HCl and the strong base is NaOH. As both are completely dissociated in the aqueous solution, the reaction between them may be written as Na positive plus OH negative plus H positive plus Cl negative react to form Na positive Cl negative plus H2O. Cancelling out the common ions on both sides, the above reaction reduced to H positive plus OH negative is equal H2O. Those neutralization may be defined simply as the process in which S positive ions given by acid combine with the OH negative ions given by the base of form unionized water molecules. As 1 gram equivalent of any strong acid in aqueous solution give the same number of S positive ions and 1 gram equivalent of any strong base give the same number of OH negative ions. The neutralization involve the combination between the same number of H positive ions and OH negative ions. Hence, the heat of neutralization of a strong acid with a strong base is always the same. Salt hydrolysis. It is defined as the process in which the salt reacts with water to give back the acid and base. Salt plus water is equal to acid plus base. Depending upon the relative strength of the acid and the base produced, the resulting solution is acidic, basic, or neutral. These observations are also explained on the basis of Arrhenius theory. Discuss the limitation of Arrhenius theory. Number 1. Arrhenius suggests the ionization of the electrolytes take place when dissolved in water. However, X-ray study have shown that many such electrolytes are already in the ionized state. As an electrolyte can conduct electricity even in the molten state, it shows that the dissociation of the electrolytes take place even in the molten state. As such, the function of water could not be explained by Arrhenius theory. The most serious objection against the Arrhenius theory was its failure when applied to strong electrolytes. Ostwald dilution law, which is derived on the basis of Arrhenius theory using the concept of ionic equilibrium, fails for the strong electrolytes. Example, a constant value of the dissociation constant K is not obtained. The degree of dissociation alpha of strong electrolytes calculated from conductance measurements alpha is equal to lambda c by lambda naught was found to be different from the calculated from colligative property. Strong electrolytes are almost completely dissociated even at moderate concentration. Example, alpha is equal to 1 or 100% at all concentrations. Hence, Arrhenius views that conductance increase with dilution because the dissociation increase is irrelevant in case of strong electrolytes. The increase in conductance with dilution must be therefore due to some other factors. Give the sum point of difference between metallic and electrolytic conductors. The main points of difference between the two types of conductors are given in the below. Metallic and electrolytic conductance. Metallic conductor. In metallic conductor, the electricity is conducted by the flow of electrons from negative potential to a positive or less negative potential. Electrolytic conductor. Here, the electric current is carried by the charged ion moving toward the positively charged electrodes. Metallic conductor. No chemical change take place when a metallic conductor is conducting electricity. No new product are formed. Electrolytic conductor. Conductor of electricity by electrolytic conductor is accom- accompanied by some definite chemical process with the evolution of some gases or deposition of, of some metals at the electrodes. Metallic conductor. In metallic conductor, temperature has the effect of decreasing the conductance. Example, conductance of a metallic conductor decrease with the increase of temperature. Metallic conductor become pronounced at low temperature. This is because at low temperature the kernels of the atom have the least vibration and offer the least resistance to the flow of electrons. Electrolytic conductors. In electrolytic conductor, the compounds, the conductance increase with the rise of temperature. This is due to increase in the mobility of the ions and increase in the degree of ionization of the electrolytes. What is meant by electrical resistance and electrical conductance? Resistance, the law that give exact relationship between the resistance, the current and voltage is called Ohm law. It states if to the ends of a conductor of voltage E is applied and a current I flow through it, the resistance R of the conductor is given by E by I. Current is generally measured in amperes, whereas voltage is measured in volts. If 1 ampere currents flow through a conductor when a voltage of 1 volt is applied to it, the resistance of the conductor is taken as 1 ohm. Mathematically, the law can be put as R is equal to E by I. All electrolyte solution like metallic conductor obey Ohm's law. Conductance, the reciprocal of the electrolyte's resistance, is called the conductance. It is usually represented by C, though C is equal to 1 by R. It is a more common practice to speak of the conductance of the solution rather than its resistance units. The unit of conductance are Siemens or ohms inverse or ohm MHO. Explain the term specific conductance. It is the known that resistance R of conductor is directly proportional to its length L and inversely proportional to its area of cross section A. R is directly proportional. L by A. R is equal to P into L by A. When P is a constant of pro- proportionality called specific resistance or resistivity, its value depend upon the material of the conductor. The reciprocal of resistivity is now specific conductivity is simply conductivity. It is denoted by K. Thus, if K is the specific conductivity, when C is the conductance of the solution, then R is equal to 1 by C and P is equal to 1 by K. Substance the value of R and P small p in equation 1. 1 by C is equal to 1 by K into 1 by A. K is equal to C into 1 by A. Now, if L is equal to 1 centimeter and A is equal to 1 square centimeter, then K is equal to C. Hence, specific conductivity of a solution is defined as the conductance of a solution of 1 centimeter length and having 1 square centimeter as the area of cross section. Alternatively, it may be defined as conductance of the centimeter cube of the solution of the electrolytes. This is illustrated in figure. If the volume of the solution is V centimeter cube, the specific conductivity of such a solution at this dilution V is written as Kv. Resistance of specific resistance. Resistivity of specific resistance small p. R into A by L is equal to ohms centimeter square by centimeter is equal to ohm centimeter. Specific conductivity K is equal to 1 by small p is equal to 1 by ohm centimeter is equal to ohm inverse centimeter inverse or ohm inverse centimeter inverse or S centimeter inverse. What is meant by equivalent conductance and molar conductance? Equivalent conductivity of a solution at a dilution V is defined as the conductance of all the ions produced from 1 gram equivalent of the electrolytes dissolved in V centimeter 3 of the solution when the distance between the electrodes is 1 centimeter and the area of the electrodes is so large that whole of the solution is contained between them. It is represented by lambda equation relationship between equation equivalent conductivity and specific conductivity. Then equivalent conductivity of a solution is calculated from the specific conductivity. The relation between equivalent conductivity and specific conductivity may be obtained as follows. Consider a rectangular rectangular rect, rect, rectangular vessels with the two opposite walls on centimeter apart and made of some metal sheet so that they act as the electrodes. Case 1. Suppose 1 centimeter cube of the solution containing 1 gram equivalent of the electrolytes is taken in the vessel. The conductance of the solution will be its specific conductivity. Further, 1 centimeter cube of the solution taken contain 1 gram equivalent of the electrolytes. The conductance of the solution will be its equivalent conductivity. Thus, when 1 centimeter cube of the solution contain 1 gram equivalent of the electrolytes is considered, the equation conductivity is equal to its specific conductivity. Case 2. Suppose 4 centimeter cube of the solution containing 1 gram equivalent of the electrolyte is taken. The conductance of the solution will be still equal to its equivalent conductivity at the dilution button. Now there will be 4 cubes each of value 1 centimeter cube as shown figure 10.2. Uh, the conductance of each 1 centimeter cube of the solution is equal to the specific conductivity so that the total conductance of the solution example equivalent conductivity is 4 times the specific conductivity. Equivalent conductivity is equal to specific conductivity into V. Molar conductivity. The molar conductivity of a solution is defined as under the molar conductivity of solution at a dilution. V is the conductance of all the ions produced from 1 moles of electrolytes dissolved in V centimeter cube of the solution when the electrodes are 1 cent 1 centimeter apart and the area of the area of the electrodes is so large that the whole of the solution is contained between them. It is usually represented by mm, lambda m. Relationship between molar conductivity and specific conductivity. Molar conductivity is related to the specific conductivities are follows. Molar conductivity, specific conductivity into volume in centimeter cube containing 1 mole of the electrolytes, when K is the specific conductivity and V is the volume of the solution containing 1 moles of electrolytes and C is the molar concentration unit. Vm lambda m will be ohms inverse centimeter square mole inverse or as centimeter square mole inverse bracket of or mole inverse centimeter square mole inverse. Thank you.